Hi, the chapter 13, the logistic regression. So we have studied several the regression models, and I mentioned that we need the different model for different type of the response and predictors. So if the y is, so the chapter 13, so the deal with the model when the y is categorical, to be exact, the y is the binary, and x is continuous. So that is, for example, the y is the outcome, the medical outcome, such as the patient has died or the patient is alive, or the y is 1 is malignant and 0 is benign. So in general, the 1 is success and 0 is failure, and x is continuous. But in the same way as the multiple linear regression model, the categorical x is also the possible. So this is chapter 13. So chapter 6 and 11, that we thought about the case that y is continuous and x is continuous. If we think about the dummy variable, that is indicator variable, it can also deal with categorical data. And chapter 7, the y is continuous and the x is strictly categorical. So chapter 8, the chi-square test, the Fisher's exact test, we have the categorical y and categorical x. Actually, it's not a regression model. So now that we can see what the chapter 13 do. And when y has the more than 2 values, that we don't deal with the model in this course, but that we study such models in other courses, such as the STAT 5820. Usually it's offered in winter semester, or STAT 6840. This is good course to take after 1 year after 5030. Usually it's in the fall semester. Yeah. Excuse me. And this chapter only discusses the very basics of logistic regression. So if you would like to know the more details, so one easy reference is the Princeton University's lecture note. So this was written very well, and it's accessible for free. So it's nice to read it if you want to know more about it. And another one is the textbook for STAT 6840. Actually, now that you can start reading this textbook, and it has more explanations and more techniques for diagnosis the logistic regression and the more generalized models. And the first one is a kind of the classic book, and this is a little bit more difficult and theoretical, and the Makarov and the Nelder's the generalized linear model book. And chapter 13, okay, so the slides for chapter 13 that do not follow the sections of our textbook, but basically it covers all materials in that textbook. Okay, so this section, the 13.1, the generalized linear model. So think about the case that y is binary, y is either 0 or 1, and consider to regress y on predictors x1 to xp, as well as intercept. So the linear model was this. And still, we know y values and x values. So what's the problem with linear model? The problem is the y is binary, so we cannot assume the epsilon follow the normal distribution. Right, so y can take only 2 values. So once, okay, so these values are determined, so epsilon can have only 2 values. Certainly, it's not distributed normal. So if this value is 0.8, then y is either 1 or 0. So epsilon is either 0.2 or negative 0.8. So it's a problem to fit the linear model. So how to do that? Okay, so at first we rethink about the y. So y is either 1 or 0. But the statistical way to think about data is that the variables, the data are realization of random variables. So even though this is just a sequence of 0 and 1, we think of this is a realization of random variable y. So we can think about probability of y is equal to 0 and the probability of y is equal to 1. So this y is equal to 1 is the success probability. So we rather explain the probability of y is equal to 1, and we denote that as the pi. So our model is pi is equal to the linear combination of the intercept and x1 to xp. So pi should be the closed interval, the 0, 1. Actually, this model, logistic model, think about this probability is always in between 0 and 1. So we don't consider the case that the probability is 0. But okay, so that is the first idea. So basically, this logistic regression model does not have the error term, but the left-hand side is just the expectation or probability. So this probability of y is equal to 1 is also the expectation of y, because y is either 0 or 1. So probability of y is equal to 1 coincides with expectation of y. And another problem is that if we think about the linear combination of the intercept and x1 to xp, so this basically ranges from negative infinity to positive infinity. But this pi is probability, so it ranges from 0 to 1. So we have some trouble. So we think about the function f from the 0, 1 to entire the real numbers, that's a space of entire real numbers, negative infinity to positive infinity, so that this model that works good. So in this way that we can say this. So typically, suppose the larger x1 means more success. Then if x1 gets larger and larger, still the probability of y is equal to 1 should not exceed 1. But it approaches to 1, such as 0.9 or 0.99. So if we think about this function y, f, then we can model this situation well. Yeah. So in general, we can write the f of expectation of y is equal to the linear combination of 1 to xp. We can denote this as the x beta. So x is basically maybe I would say x transpose, or x is this vector, and the beta is the beta 1, oh sorry, beta not beta 1 up to beta p. So this is called the generalized linear model. So the f is invertible, so expectation of y, or probability of y, is equal to 1 in our case. This is equal to f inverse of x beta. So this is a little more intuitive. So suppose we have only one x, then the fixed beta values, then x gets larger, maybe probability of success gets larger. And what's the curve? The curve is typically like this. So larger x values, more success. But probability just approaches to 0. So we use this curve. So this is basically f inverse. So maybe this is probability. So maybe I would say expectation of y, then E of y is equal to the f inverse of x beta. Okay, so this is just image. Actually, this is combination of intercept and the term over x, but this is the image of f inverse. Yeah, so maybe to be exact, this should be x beta. Yeah, and so now that we think about what is f, the function f, and actually we have to hand pick this f. So we don't estimate f, but we give just the specific f. And just for convenience, we want to use the convenient f to estimate this model. And often we assume the f of pi is equal to logit function of pi, that is log of pi over 1 minus pi. So pi is success probability. So 1 minus pi is a kind of failure probability. So the ratio of success to failure. So that is called the odds ratio. So this is the log of odds ratio. So f of pi is often assumed as this. If pi goes to 0, then this goes to negative infinity, log of 0 over 1. So this goes to negative infinity. Pi approaches to 1, then this quantity, pi over 1 minus pi, goes to infinity. So that means log of that is also going to infinity. So yeah, so this function is, okay, so basically, yeah, so this satisfies the condition. So the pi is 0 to 1. Then negative infinity to positive infinity. And it becomes 0 when pi is equal to 1/2. Pi is 1/2, that is log of 1, that is 0. So actually this is 1/2. Asymptote is here, and also pi is equal to 0. Logit of pi. And another function is the f of pi is the phi inverse of pi. Here, the phi is the CDF of standard normal distribution. So you can see that the CDF is generally the increasing function on the entire real space. And range is between 0 and 1. So if we think about the inverse CDF of any probability distribution, then we can define that function as f of pi. Yeah, so normal distribution. Good thing is that it has more natural interpretation statistically or probabilistically. And the downside is that phi inverse does not have specific analytic form. So it's not as easy as calculating log of pi over 1 minus pi. So there are some models which deals with the multivariate, the binary response. So we have two outcomes. One is patient dies or not, and does not die. And the other is malignant or benign. So we have two variables. So in such a case, actually the probit model is more convenient because we can extend the concept to multivariate normal distribution. Yeah, and the first one, the f of pi is logit of pi. So this is called the logit model or logistic model, or logit regression model or logistic regression model. If f is phi inverse of pi, the inverse, the CDF of standard normal, it's called probit model. And both have inverse function because it's monotone increasing function on 0, 1. So f inverse of pi is exponential of pi over 1 plus exponential of pi. So you can, this is just a quick algebra, so you can derive this from here. And obviously, the second one, the f of pi is phi inverse of pi. So f inverse of pi is phi of pi. So this is for probit model. So this is the integral, the 0 to pi, then the standard normal density, 1 over square root of 2 pi, square root of 2 pi, I'm just terrible writing, 2 pi, and the exponential of the negative x squared over 2 and dx. So phi of x has the expression, but the phi inverse of x does not have an analytical expression. And in this chapter, we focus on logistic model, and we don't talk about probit model. So logistic model, it's more convenient in the sense that both the F and F inverse have analytical form. And the logistic regression is more robust against outlier compared to probit regression. So if we have, suppose the, if we have outlier such as, okay, so maybe I would say the leverage point, suppose the larger X means the more success probability, higher success probability. But with very large X, one observation with very large X actually failed. And in such a case, the logistic regression is more stable than normal, the probit regression. Because the tail probabilities are different between logistic and probit. So curve. So for logistic curve, the approach is slowly to 1 and 0. And the probit model, the approach is faster. So if the contradictive happens with very high success probability, we failed, or very low success rate, we succeed, then the likelihood function is unstable and the estimation is difficult for probit model. But for some data, probit model fits better. Yeah. So this is an overview of logistic regression model.